Hello, my name is Patrick Kelly. I'm a graduate student in the physics department at California State University, Fresno. Today I'm going to be presenting on the supersolid phase in simulated cold atomic Fermi gases. We performed a Quantum Monte Carlo study of a two-dimensional cold Fermi gas on an optical lattice, which can be experimentally realized with laser standing waves. At half filling, when on average one atom occupies each lattice site, the system displays an intriguing supersolid phase, a superfluid with a checkerboard density modulation. The static and dynamic properties of this exotic phase of matter were calculated. Cold atomic gases can serve as a model for other interesting and seemingly unrelated systems, such as superconductors and the interiors of neutron stars. It is believed that superfluidity plays an important role in explaining the properties of these systems. Consequently, our research has relevance to a wide range of topics in physics. So first, I'm going to give an introduction to cold gases on optical lattices. Then I'm going to talk a little bit about theory, especially the Hubbard model. Then I'm going to talk about our experimental results. First, our calculation of the static properties, then the dynamical properties. And then I'm going to talk about our conclusions and future directions we might go with our research. Collections of large numbers of bosons or fermions can be cooled to low temperatures. These are cold atomic gases. We cannot easily access the insides of exotic systems such as superconductors or neutron stars. Realized in the lab, cold atoms provide an excellent opportunity to study many-body physics. Exotic phases of matter in which our usual intuitions about solidity and fluidity overlap can be explored. Experimentalists can prepare a cold atomic Fermi gas by combining and organizing clouds of cooled lithium or potassium atoms with interfering laser beams. It is also possible to embed the gases in an external field. We focus on fermions moving on an optical lattice, which can be realized with standing waves of laser light. We use computer simulations to study a cold atomic gas on a 2D optical lattice and tune the parameters of the Hamiltonian in such a way that we can explore the intriguing supersolid phase that is formed. Our most important result was a calculation of the dynamical structure factor, which you can see here. We modeled the system using the Hubbard model. The model is relatively simple, but no analytical solutions exist. We studied the attractive case where the potential energy is less than zero. And here's the Hamiltonian written in terms of the kinetic energy and the potential energy, which are written out explicitly here. The kinetic energy part is responsible for modeling the motion of particles as they hop from one site on the optical lattice to another. The potential energy part allows for particles with opposite spins to interact, bind, and form pairs. Two particles with the same spin cannot exist on the same lattice site. This follows from the Pauli exclusion principle. In our research, we use Quantum Monte Carlo to solve the Hubbard model implemented on supercomputers. Doing this, we can obtain exact results. We studied a system that is at half filling, when all lattice sites are occupied, and that is spin balanced, where half the particles are spin up and the others are spin down. This is illustrated here. So now I'm going to talk about our results. So first, the density correlation. If you imagine sitting on a particular particle, The density correlation is the probability of observing another particle a distance r away from you. At half filling, the system organizes into a structure with a periodic density modulation. This is a characteristic property of a solid. You can see that here. You're more likely to observe a particle at some sites rather than others. Now the pairing correlation. A spin up and spin down particle can meet at a lattice site, bind, and form a pair. The pairing correlation is proportional to the probability of a pair traveling a distance r from the site where it initially formed. Notice the function converges to a small value, but does not go to 0. You can see that here. This tells us the particles and the pairs they form are quite mobile within the system, a characteristic property of a superfluid. This property, combined with the density modulation mentioned earlier, confirms that we have indeed found a supersolid on the lattice. So here's our most important result, the dynamical structure factor. The plot gives our results for the dynamical structure factor SQ omega, whose expression is given explicitly here. This function gives the distribution of possible exchange momenta and energy between the system and a probe. It measures the probability of the system's momentum changing by q units and the energy changing by omega units after being probed. The results were obtained after applying analytic continuation methods to the results of our Quantum Monte Carlo calculations. The high peak at m equal to pi pi, that's this point here. You see it's especially dark. That indicates that it's a very high peak. Indicates the system is a solid because it causes zero energy to impose that density modulation on it. Essentially, the system already has that wave-like structure as its most preferred state. The static properties have been calculated before for this system, but these results for the dynamical properties are new. We measured the dynamical properties of the supersolid phase in a 2D cold atomic Fermi gas. Our research should guide experimentalists through some of the difficulties in creating these phases in the lab. In the near future, we would like to characterize the stability of the supersolid by attempting to melt it. This may be achieved by removing some of the particles of one spin, violating the condition for half filling. So that's my presentation. I'd like to thank Dr. Vitale for mentoring me and guiding me through this exciting, interesting research. And I'd also like to thank Annette Lopez for assisting me with this research.